So have you solved the problem how to avoid divergency, infinity? So let me remind, what we have discussed last lecture are resonances. And we first presented kind of phenomenological description of resonances, just using the fact that resonances are usually fastly decaying particles, and you know what is a decay law for the particles. On the other hand, everything should come from a fundamental theory, which means from field theory as we understand it now. And so we need to get also this resonance behavior from the field theory. And that's quite obvious, because in the field theory we have these propagators of particles, and they indeed have the pole when square root of s is equals to the mass. So let me again remind, if we write the amplitude of the process when we have, say, annihilation of E plus and minus into J psi, and in final state have mu plus minus, we need to attach to this line propagator of J psi, and therefore the amplitude will be proportional to the propagator, which is in this case is S minus Q minus M squared. Since this is S channel, and therefore the form momentum of J psi is precisely square root of S. So it's given by S, right? So Q squared here is S, which is positive, and therefore we have explicitly the pole in the propagator. This is good, which means that we can explain enhancement of amplitudes and therefore cross sections, because cross section is just moduli square of this, right? And so we can explain why production of the particle will show up as this peak. So the problem is that we have this pole, and the question is how to eliminate it, right? So what is proposal? How you would approach this problem? So we show this will be like this square root of S, and here is the amplitude, but we can also write the cross section, because cross section is proportional to the amplitude moduli square. And of course, this doesn't eliminate the pole. So,
you need a cutoff. You need a cutoff, maybe. Cutoff.
Oh, now we are in the field theory.
No, but when we say that S will be equatoms and 0 square, we will use the particle at rest. But this is contradict with Heisenberg principle of uncertainty. So we will never do.
No, it doesn't eliminate. Yes, so actually this is not at rest, because everything is here. So that's Lorentz invariant, right? So you can consider any reference frame, and this is the mass of the particle. So this is Lorentz invariant. It doesn't help, and therefore you can even imagine that they're moving.
With line, like we have to add something in the numerator, so we don't have the pole.
That's kind of you saw from the we need to add something to the denominator, but
I will say, like first this production will be mediated by the electromagnetic interaction in the quark level.
No, let's do this at this level, because it doesn't change things. So going to another level, we need to explain this at this level, because we saw the peak at this level, and the peak is due to mass of J psi, not at quark masses, right?
I was reading a little bit, maybe there is a term called self-energy of the particle that goes there. We would say there is.
Okay. So you want to say something?
Yes, I would say maybe it's similar to the GIM mechanism, where we encountered something like that, but there is another possibility that makes it minus
No, no. Well, so this is what you started to tell, and actually it was also comment yesterday that maybe there are some other diagrams, but which type of the diagrams? And indeed, once you are in quantum field theory, you're just doing straight and correct computation, and you should get correct results. That's no question. At least for time being, we haven't found any kind of fundamental problems with this. And so let me focus on propagator, which actually produces all the problems. We have this propagator of J-psi or any resonance. I mean, that's kind of similar system. But being in quantum field theory, we need to add high-order diagrams for this. In particular, the diagrams of the following form. When we insert here some other particles, which are kind of emitted and absorbed. The simplest example in this case is that J-psi can actually be transformed into, again, but virtual E plus, E minus, or mu plus, mu minus. Okay, so the same diagram is. This is automatic because since this coupling exists, we need to entertain all type of the diagrams which actually are produced by this interaction. And in particular, what may happen that your J-psi is transformed to virtual E plus E minus pair or mu plus mu minus pair or whatever it can be transformed. Everything. Hadrons, everything. And so we will get this type of the diagram. On the top of course, other diagrams, because for instance, it will be diagram and we have gamma, which is emitted from here and absorbed here, but this diagram will not have any divergence of this type, and therefore it cannot cancel this divergence. Now, well, actually we need to add also higher order corrections like this. Plus 3 loops, 4 loops, 5 loops. Let us focus on this type of the diagrams. And then the total propagator can be written as 1 minus S minus M0 square. That comes from the first term. Now the second term, what we are writing here, we have here propagator of J-psi, or this resonance. So we write again S minus M0 square. Then we will write something which describes this loop, and then second propagator, S minus M0 square, plus, and it is clear, so what you will get is then the series in which you have this kind of common you will add. So the next term it will be this block squared, then in a cube, etc. Okay? So P is what we call vacuum polarization operator. So we can actually easily make to sum all these terms, and you can convince easily yourself this S minus M0, we can put it out, and then what is inside is 1 plus P S minus M0 square plus this term, as I said, squared, etc. And so we will have series in the power P S minus M0 square n. Okay? So it's easy to, and you probably know what is the sum in this case. And the sum will be 1 S minus M0 square multiplied by 1 minus P S minus m0 squared, right? So that's the sum, which can be written then 1s minus m0 squared minus this polarization operator. So just multiply it. Agree? Okay, so you see something appears in addition in the denominator. Questions? Yeah.
Are those the only types of diagrams that are allowed? So we add all of them? Yeah.
No, so there are also other diagrams, but they have not this pole. So I kind of focused on the diagrams which are useful for me. But the total cross-section will also contain some other diagrams.
Do you prefer such types of diagrams where should have high probability and, for example, the one which have a lot of loops, like because we sum until infinity, so it should have very lower probability. Do
Yes.
we preserve this?
Yeah, so but I just selected subset of the diagrams. Of course, there are some other diagrams which are contributing to total cross-section, which is even bigger than we will see that this one. But all these diagrams have these divergences. So if I'm sitting in divergences, those are dominant contributions in divergent point. Okay? So what is this P? Polarization operator. It can be written as PR, real part, in general it's complex, plus IP imaginary, and therefore the propagator equals 1s minus m0 squared plus, that's minus p real, and minus IP imaginary. Now, it's not accidental I put here m0, because this is bare mass, the mass which I have introduced in the beginning in my Lagrangian. But now I will denote m square, m0 square minus or plus PR. So this is what we call renormalized mass. So this is the mass which includes corrections of certain types, right? So this is renormalized mass. And therefore my D becomes 1 s minus m squared minus IPI, and then D moduli square, and eventually when I'm computing probabilities, I eventually compute moduli square of all the elements. That will give me 1 s minus m squared plus p imaginary square. And this should be squared. So now clearly we have eliminated pole, so there's no divergency. And now let us clarify what is this P imaginary. And at this point, actually I give, this year I have 2 lectures less, and therefore I'm trying now to squeeze material. I give this derivation explicitly, but now I'm just outline what is this. So to find what is Pi, that is imaginary part of polarization operator, I will use optical theorem. Which appeared in optics, but then it was actually generalized to various other systems. So what is this optical theorem? Optical theorem is the consequence of unitarity of S matrix, Who knows what is actually optical theorem? Somebody studied this somewhere in some course. So what is S matrix? S matrix is formed by matrix elements between final and initial states. So that's Fi. And you should consider all the space of initial and final state. So that will form your essentially infinite matrix. Okay? Now, S here is S operator. Which is given by T ordered exponent. You probably this learned already in quantum theory, right? So then the integral over dx to the fourth over Lagrangian, obviously. So unitarity means that S dagger S equals unit matrix. Essentially, this is expression of the fact that if you have system, then the total probability to find your system after interactions in some state is 1. So, which means that it doesn't disappear completely. So that's the physical meaning. And explicitly using this definition of S matrix element, we can write this as the sum over n SFN multiplied by SNI dagger, and that should be delta Fi. So this is explicit expression for unitarity of S matrix. What is important here that you need to make summation over all possible states. Possible means that all the states a given initial state can be transferred. So of course you should not include here when your proton is transferred to electron, right? So you violate electric charge. But all possible transitions should be taken into account. Now what is optical theorem? Let me just write it and then I will explain. So essentially you can get optical theorem writing this S as 1, which is kind of means that system doesn't transfer to anything. It's again the same as an initial state, plus T matrix as we introduced this. But I will skip, so I had this derivation in the previous years, but now I have no time for this. So optical theorem means actually, this is a very important tool to make computations of the diagram. So let's keep this in mind. Maybe it will be interesting for you. So imaginary part of amplitude of elastic process an elastic process means that initial state is transformed to the initial state, same state. So it doesn't mean that there is no interaction. Still you may have some interactions, but you have initial state which is transformed to the same state in the end. So according to optical theorem, this imaginary part equals up to some kinematic coefficient which depend on specific process equals total probability of process when your initial state is transformed to everything it can transform. And of course, you need to sum up here over all possible states. You already have some feeling probably why it comes from this unitarity condition. So here you have imaginary part of specific process when you have essentially no change of the content of your state. And here you need to consider total cross-section on your initial state is transformed to everything it can transform. And what is important, you need to sum up over all these things. Well, actually, let me give you some kind of intuitive explanation of this optical theorem. Well, probably I will write explicitly that imaginary part of the amplitude I, so that's process of transition of state I to state I, equals K, and here's the sum over N of probabilities of the transition I to N. So that is, if you want, that is formalized expression of this optical theorem. And K is kinematical, known kinematical factor. It depends which kind of the process you are considering. What is your initial state? If it is one state, one particle, two particles, three particles. So that determines quite definitely what is this coefficient K. Now, intuitively, this can be explained in the following way. What we have on the left-hand side is imaginary part of the following process. When you have initial state, and it is transformed into the same state. This is initial, this is the same. And you compute imaginary part of this amplitude. Okay? Now, what is staying on the right-hand side can be written in the following way. So again, that's up to coefficient K. And what is staying here is the sum over N. And then what I need to sum is the following. So it's probability of the transition, so which means I have the same initial state, which can be transferred, can be transferred to anything, and then I compute moduli square. Right? So this is the probability which I compute. So I need to compute this amplitude and then compute moduli square. Now, what is this? I can write this as K, sum over N, and then I can write here this diagram multiplied by the same but conjugated, right? Huh? Okay. So, and now this is nothing but I will just invert this diagram. So what I will get is that this is equal K, and this is the sum, and this is this. Right? So you may have some kind of feeling that this thing should be connected, because what is written here is essentially a kind of cut of this diagram. Agree? And so to have this equality, you really need to sum up of all possible this internal states, and then you will get what you have here, because here you sum up over all possible intermediate states. But again, I can give you the exercise for you. It's not a big problem actually to derive this relation. So imaginary part of the amplitude of elastic process, which means that the same initial and final state, equals total cross-section, total probability of the process when you have the same initial state, which is transformed to everything. Okay, so this N, and then I make summation over N. Now, for a single particle, which will be important for us, if you have initial state and initial state we have just one particle, what we will have? On the left-hand side, we will have imaginary part of such a diagram. This is A and this is A. And on the right-hand side, we will have K moduli square of this diagram. When particle A is transformed to everything it can transform. So actually, this is nothing but our imaginary part of polarization operator, right? And what is this? What this diagram corresponds to?
Total cross section.
So we have a single particle in initial state, right? Cross section usually we introduce when we consider scattering. At least two particles should exist, right? In initial state. But what is this? Right, so this is just decay. And it's nothing but total decay. What is important because we need to sum up all losses. So it's total decay rate. This is important, remember this, total decay rate of particle A to everything. So that which means that imaginary part of our polarization operator, let me write this, AA, is given by gamma, a total decay rate, and this K factor is square root of S. Yeah, that should be easy to, but I have no time to make this diminution. Well, actually, it's an important tool to make computations. For instance, if you want to make computations of some cross-section, total cross-section, you can compute just imaginary part of this diagram, okay? And people are using this. And usually it's easy to compute imaginary parts because then you need to pick up from propagator something which is actually gives you delta function. And therefore, this integral is usually quite easy to do. So keep in mind if someone wants to, will do in future some computations of total cross-sections, one can use this trick. So this is what is important for us. And now let us come back to our expression for propagator of resonance. Now what we have, that cross-section is proportional to, no need to put this 1 over S minus M square. And here I put S and gamma square, gamma square. Because here it was P imaginary part square. So, extremely important result is that the widths of your peaks will be determined by total decay rate, not particular decay rate, but total decay rate of the particle. So, now we have no pole, and our dependence cut. Dependence on square root of S. And from this formula you can get easily that the width of the resonance is given by gamma. And this is what is important, total decay rate. In our example, total decay rate of J psi. So again, let me remind, although we are discussing particular channel, like for instance, E plus, E minus to mu plus, mu minus. So here J psi decays into mu plus, mu minus. But the width of this process, or cross-section, will be determined by total width of J psi, and not just this particular. Remember this, and this is actually a very clear way why we get this result. So you can measure using particular channel, so particular initial and final state, you can measure the total decay rate of particle. Yeah?
This expression from field theory calculation is very much similar to what we had in the quantum mechanical.
Yeah, so,
formula,
yeah.
But it's not quite the same. We have an S factor in
Yeah.
terms of decay rate.
Okay, so this is final point I want to do. If my resonance is not very wide, so that gamma is much smaller than m, then it's easy to see that this expression can be reduced to 1 square root of s minus m square plus 1/4 gamma square, and that is actually exactly leads to what we had before. So it's also here 4m squared. So how to do this? You just write that s minus m squared can be written approximately, can be written as square root of s minus m square root of s plus m square, and here you can say that square root of s, if you are sitting in resonance, is approximately m, and so then you get such an expression.
And here M is not bare mass.
M is physical mass. This is what we are measuring.
But in our calculations we put the real part on top of the M, like bare mass and what was the
Yes, real part of this polarization operator. This is what produces renormalization of the mass, not imaginary part. Imaginary part, you know, that produces for us this additional term which removes the pole.
So,
And it gives you, so what happens that a real part actually gives correct position of the peak, and the imaginary part gives the width of this resonance.
correct means what we measure from experiments are reproduced through M plus real part of the.
Yeah, of course. Yeah, sure. So we are not measuring, in the same way as a coupling constant, we are not measuring some coupling constant in the lowest approximation in your Lagrangian. We are measuring the coupling after summation of all the corrections. By the way, I want to add another important consequence of this asymptotic freedom and dependence of QCD, remember, which decreased, is a possibility to construct grand unified theories in which all the couplings have at some point equal quantity value. So what happens is that strong coupling constant decreases with Q squared, electromagnetic coupling increases, and at some point they meet each other, so they become equal. This is what determines the scale of grand unification. So that opens the way to unify interactions. So, yeah.
Here we can calculate the total decay rate. So, but the total decay rate is equal to the summation of all decay rates of all possible decay diagrams, or it's equal to the probability of each diagram or each decay to happen multiplied with its decay rate, and we sum them up. Because if we have a decay rate which is favored to happen, most probably the decay rate of the total decay rate of the particle will be more or less equal to that.
Of course, if one mode dominates, then that will give the main contribution to gamma. So yes, you need to compute to find explicitly, theoretically, to compute. You need to compute probabilities of decay for each individual channel. Yes, different channels have different probabilities. Then you need to sum up. So, for instance, in Z0 decay, practically all the modes of the decay have comparable value. Of course, they are very rare, but the main modes they have, and there are many of them, they have a comparable size of gamma. So, you need to compute all of them and sum up.
For example, in different experiments of different channels, they found that the width are different. The first thing to think about is there is another resonance than there is, because we always would have the same width with different channels, the same total degree.
Yes, yeah.
If there is a variation of the width in different experiments, the first thing.
Well, again, are you talking about the same particle or
Yeah, the same.
the same resonance? Okay. Then in all the experiments, the width on the half of the height is the same, independent on channel. When you add the channels, what's going on? So your peak becomes higher, but the size and the half of the width is the same. And this is the proof, actually. You see, that's the proof, because imaginary part of polarization operator, which you put, is related to the total decay rate. And this follows from unitarity, from this optical theorem, which in turn is the consequence of unitarity. Okay? Now let me do the following. You see, this year I have 2 lectures less than before. It's not because of me, but I don't know, the organizers decided that the number of lectures will be smaller than before. So before I had some 24 lectures, now it's 22. And so I thought which material I should throw out. And what I have decided, I decided to remove material which is actually is based to a large extent already on known standard model. So that includes, for instance, real discoveries of W boson, Z boson to a large extent, and Higgs boson. So everything, all these things already were discovered after standard model has been established, and coupling constants, for instance, of these particles follow from the standard model. So a right way is to first introduce standard model and then to discuss these discoveries. I'll just make very short summary, okay, of these discoveries, but that should follow in the course of the standard model. I'll check again. I don't know who will give this course next semester. She's saying that should be to a large extent discussed in this course. So one comment is about intermediate bosons. So it's summary of other discoveries of elementary particles and important discoveries. First, intermediate bosons. And here we will talk about W and Z, and maybe a little bit more about W, because that was already introduced before standard model, and already Fermi thought that the theory of weak interactions is not actually the product of 2 currents, as he introduced, but in fact follows from something which is similar to electromagnetic interactions. And 4 fermions or 2 currents are interacting not in a single point, but in 2 different points, and therefore there is an intermediate particle, intermediate boson, which carry information from one point to another point. Okay? So for this, Fermi has written this famous, let me put effective Hamiltonian, which is GF square root of 2, and then the product of 2 currents. G mu times G mu, and dagger. And what are these currents? Is actually the sum over all currents which we have introduced before. Right, so it's I. And this is sum which includes electron current, muon current, tau current, current with U quark, tau, current with charm quark, current with top quark, with all this mixing. So everything is sitting here. And this is the Hamiltonian which describes. So instead, and already Fermi know this, and thought about this. A more fundamental Lagrangian, in analogy with electrodynamics, is actually this. So we have this current, which should couple with this intermediate boson, plus emission conjugate. So, properties of this W boson are clear, so W boson should be massive. Otherwise, the interaction would not look like a point-like interaction. So, the mass should be at least bigger than the highest energy till which the interactions look like a point-like interactions. So, it should be charged because it couples with charge current. It should have spin 1 as a photon, as electromagnetic interaction, and it should violate parity. In contrast to electromagnetic interactions, so coupling of photon is coupling with vector current only, and here we have current with vector and axial vector currents. Now, how about the coupling constant? The diagram on the right-hand side, I mean, it would be nice to write it here, but so you can continue probably. This diagram can be written explicitly as G2 square root of 2 square, and this is the consequence that we have two couplings, we have two vertices. And now we need to write something which corresponds to W boson, that is propagator of W boson. And I will write this in the simplest form because what you need to write G mu nu minus Q mu times Q nu over the mass of the W boson, these factors which I'm not interested for the time being, and I can explain why I'm not interested. Okay? Now, if Q square is much smaller than the mass square, mass of the W boson, I can neglect this Q, and therefore what I will get here is G2 square root of 2 square 1 over mass of the W boson square, and I will not care much about this sign up here. So, and then I will get, of course, this product of currents. So it's actually what I should write here is G mu, then the G mu nu, let me take just one, and then G mu. So this is more precise expression of what I'm writing here. Plus these terms with K or with Q, so plus terms which are proportional to Q squared, and they can be neglected if Q squared is small. So essentially this one, and what I see that this expression is reduced to this one, precisely, if G Fermi square root of 2 equals G2 square root of 2 square 1 over mass of W boson square. Agree? So this is G, I think I should write this nu here, and then this G mu nu is just usual stanza, and that will give me, this will give me exactly this effective Hamiltonian expression which I have from this Hamiltonian. So that gives you explanation what is this G Fermi. G Fermi has dimension of mass square inverse, and that comes from this MW boson square. Now Fermi, remember, thought that this G is just electric charge, which is not correct. So in this case you will get mass of the W boson, since this is measured. If you know what is this G, you can find what is this mass of the W boson, so you will get something like 37 GeVs, which is not correct. So actually the standard model allows you to fix this G. Standard model and measurements of so-called weak mixing angle, which I will not discuss. So standard model gives you what is this G, And once you know what is this coupling constant G, you can find what is the mass of the W boson. And it was predicted that the mass should be 80, around 80 GeVs. So that standard model gives, and then mass of the W boson should be around 80 GeVs. Now let me say a few words about Z0. Existence of neutral intermediate boson is the consequence of the standard model. So Z0 was predicted actually by Gleschel, who actually introduced this structure. And what is this Z0? It's also gauge boson. It's a vector particle with spin 1 and electric charge 0. And it has couplings in particular with fermions of this type. And these couplings are different for different fermions. What is interesting that W boson has only coupling with V minus A current. Z0, in contrast, have also coupling with V plus A current, although the parity is violated. But again, that you will learn later. Now, standard model also gives the mass of Z boson as consequence of the standard model. And it gives all these couplings, GZI. So that comes from the standard model and measurement of so-called weak mixing angle. Now, one of the consequences of existence of this Z boson is existence of neutral current, because here we have neutral current. The fermion, for instance, is transformed to the same fermion. The charge is 0 here. And there is no flavor changing here at this vertices. So you have not, according to the standard model, this is flavor diagonal. Now, one of the predictions from this existence of neutral currents, and in particular process when nu mu go to nu mu, and electron go to electron, and the same diagram for antineutrino. So actually Z has even more, again, universal coupling. It couples with everything, but the couplings are different. They are not so universal as the couplings of W boson. So, according to the standard model, such processes have been predicted, and they were observed, have been observed. So that was really great discovery, and one of the points at which people start to believe in the standard model. So, neutral currents have been discovered in 1973 at CERN, and the CERN used bubble chamber, which uses transition of liquid to the gas. So they have overheated liquid, and something related is freon, something which you use in refrigerators, and then the particle ionizes, the bubbles of gas are formed, and so you can see the tracks. That's important. Actually, you can see this bubble chamber. If you go to the CERN, they put this as an exhibition, just in between the buildings. You can see they put this. You can see this chamber. Anyway, so these processes have been discovered. That is nu mu plus E, and also antineutrino go to nu mu. This is antineutrino. That was extremely important experiment. Again, the first really very strong confirmation of the standard model. Now, a few words about discovery of W and Z. W and Z bosons have been discovered at CERN, and they used proton-antiproton collider with the name SPS. So this collider is in use now in LHC complex as pre-accelerator. So protons first accelerate in this SPS and then injected in the main LHC beam. There were two experiments, UA1 and UA2. And what they have detected production of W bosons in proton-proton collisions. In particular, U quark from proton, mostly because they have, and D antiquark from antiproton can annihilate into W boson. Right? So we have this coupling. And then W boson decays into, essentially W plus, into electron and neutrino, or it can decay into muon and the corresponding neutrino. So this type of the events have been observed at accelerator. Again, I will skip all the details. And what has been measured, the distribution of these leptons charged up, because signature is very clear. Actually, you have even some photos on the desks of this in ICTP. So which means you have collision of proton and antiproton, then a lot of secondary hadrons in the final state, and the track of muon, or track of the electron, and missing energy, because this is what is taken by neutrino. So you can measure angular distribution of these charged leptons, and you can measure the energy distribution of these charged leptons, and you can compare with predictions from this process. And in this way, actually, you can measure the spin of W boson, because that determines also the angular distribution. And so everything was okay. Actually, that was some interesting story, but if you ask me, I will explain later. So that is how W boson has been discovered. And Carlo Rubbia got a Nobel Prize for this discovery. Now Z boson is even simpler. Actually, I have one exercise for you in this respect. Z0 again was discovered in the same experiment. Again, proton-antiproton collisions. And you have the following process where quark and antiquark annihilate into Z0 boson. And then Z0 can decay into E plus, E minus, or mu plus, mu minus, and after that also decay into tau have been discovered. But these are very clean, because these are particles which you can really see the tracks of these particles, electrons and muons. So in this case, the story is even simpler, because what you can construct invariant mass of E plus, E minus, or mu plus, mu minus. So the event is, again, you have proton-antiproton collision, a lot of secondary particles, and in between you have clear tracks of very high energy muon, mu plus, and mu minus, for instance. Okay? So what you do, you construct invariant mass, and as we have already discussed, you get this peak. And the peak is at 92 GeVs. So this is square root of S, which corresponds to Z0. Now this peak has been measured with very high precision. It's not just, you have bad energy resolution like in the case of J psi, and you do not see the width of the peak of the peak which you see has the width determined by energy resolution, not by real physical width of the particle. But later, at OLEP experiment, that was measured with very high precision. So LEP is electron-positron collider in the same beam where LHC is now running, but before it was this E plus E minus machine. And they measured very precisely the shape even of this Breit-Wigner peak due to Z0. They measured gamma, total width, of course you measure total width. And what is important that the total width is given by the width due to decay into 2 neutrinos. And you do not see neutrinos, right? So you do not detect, plus visible width. So this is due to decay when Z0 go to nu bar. So you can compute this thing. You can compute what is gamma nu for a single neutrino pair, and therefore measuring of this gamma total. So then gamma nu is given by number of neutrino species multiplied by gamma nu 1. I think I mentioned already this. Okay, agreed? Because the coupling with all different neutrino species of Z0 is the same. And therefore you can measure what is this n. What is number of neutrinos of different types. And therefore to establish what is the number of generations. And experimental data agree well with the 3 neutrino species. So this is one of the important outcomes of these measurements. But actually, to be more precise, so n nu is 2 point, and I don't remember precisely numbers, is less than 3. Something like 2 sigma, less than 3. So maybe it's just statistical fluctuation. So the deviation is not so big. I don't remember, it's 2, 9, because the accuracy is very high of these measurements. I can check this, I'll tell you next lecture. I forgot to take this. Another question, some people believe in this difference, and that may be indication that maybe there are heavy neutrinos and the mixing with heavy neutrino, heavy degrees of freedom, which cannot be produced in Z0 decay, and that actually explains this deviation. Now, that I think everything about Z0. Now, top quark.
How can we infer from the peaks in the measurement that there are bosons in between? It could still have been a 4-point interaction.
But then you will have no peak. Why it should be peak if there is 4 fermion interaction?
And so we can detect the boson at some.
We detect this in this way, so we do not see the track of Z0 and all W boson. But this peak, you cannot get this if you have 4 fermion interactions.
So this peak is caused by one particle that has the same square root of S.
So remember what we discussed in the beginning of lecture. So this peak is because of propagator of Z boson and Z boson, and here is Z boson in S channels, precisely what we discussed before for J psi, but now we have Z0. So again, appearance of the peak signifies that you have somewhere resonance, right, in S channel. So this is how you can explain. You cannot explain. Maybe you can invent something, but physics doesn't know other ways to.
But for W boson, we have no peak, right?
Well, we can observe peaks, but in hadron channel, we cannot observe this peak. The peak exists if you measure neutrinos, because you have in this channel you have production of charged lepton and neutrino. Neutrino is missing, and therefore the only way we can measure charged leptons. However, there are decay channel of quarks, of W boson into quarks, so you have hadrons, and if you select particular events, you can see also this resonance. Yeah.
Quarks always appears as jets.
Yeah, eventually they are producing jets. Yeah.
when this boson has been confirmed, that because
Well, I think final was in '84, so there were a series of experiments, and you asked me when, or?
when, yeah.
So at CERN, I think in the years 2008 to 84, so that's when this experiment has been done.
But actually, the Higgs boson.
Not Higgs boson, we are talking about Z boson.
Yeah, but also the Higgs boson have the mode to decay to two Z bosons.
Well, not real, because the mass of Higgs boson is lighter than the sum of the masses of two Z bosons. It can decay into virtual, yeah, and that is slightly. So one of Z bosons can be real, another is virtual.
But I mean, why
Let's do the following. I will discuss now the Higgs boson, and then you can ask questions.
Okay.
But before top quark, top, remember, was introduced. Top quark has been introduced because we wanted to explain CPU violation by Kobayashi and Moscow, and it was the third generation, which included top and, let me put here, CKM, this is a mixing combination. So top quark has been discovered, and it was a long story. Top quark has been discovered kind of several times, because first there was some announcement that top quark has mass 40 GeVs, and then it was another discovery, and finally it was discovered in '95 in Fermilab using Tevatron. And the process was proton plus antiproton go to top bar plus everything. And there are different mechanisms actually of production of this pair. And you collide proton and antiproton of high energies. The square root of S is around 2 TeVs, which is important because you collide quarks, and quarks do not care total momentum of they care only part of the momentum of protons. So you need to have high energy protons and antiprotons to have enough high energy quarks and antiquarks, right? To create top anti-top quark pair. So one of the mechanisms is this quark and antiquark annihilate into gluon, and then gluon produces top anti-top pair. So another mechanism is gluon fusion, when you have two gluons, one is from proton, another from antiproton, and they produce top quark and top antiquark in this way. So the diagram is this, and this is from proton, this is from antiproton. These are gluons. Again, these quarks are from protons and from antiprotons. Now there are also mechanisms when they produce a single top, and you may have process which is less probable, of course, U, big bar, and then you have W boson, which then produces top and big quark. So how top has been detected? Top plus anti-top gives you what? The most probably gives you P and W boson plus B minus and W plus. So this is why actually I don't discuss this in great detail, as you need to know properties of W boson. So that comes from exactly existence of this pair, which means that you have transition due to W boson from top to bottom or from bottom to top. So which means that you have, this means that you have coupling, you have current when bottom quark is transformed to top quark, and this is W boson. And this is precisely what is written here. So top can decay into B quark and W boson, and anti-top into B minus and W Yeah. So now, what is important here that you have. So this charge, this is from top plus, and this is from top minus, right? Because the charge here will be. No, this is from top minus, and this is from top plus. So the charge will be minus 2/3, and here the charge will be plus 2/3 because charge of B is 1/2, minus 1/2. Okay, so then what happens is that W bosons decay into leptonic pairs or into quark-antiquark pairs, and this also decays into neutrino and lepton and quark-antiquark pair. Here is L plus and here's L minus. Now you have different modes when this guy decay into, say, leptonic, this is to quark, or this leptonic and this to leptonic, etc. So what is important is that you need to be sure that you also produce B quarks. And this is made by special detectors, and you do B tagging. So some special silicon detectors were produced, and now the procedure is very complicated because you need to find out that B quark is produced. And this is the signature. You need to select out of many events in which you have production of 2 B quarks. How you do this? Of course, B quark decays very quickly, so you need to identify the products of the decay of B quarks. Construct the invariant mass of these products and be sure that invariant mass is 4.5 GeVs. This is what we are expecting for B quark. You need to repeat the same for W boson. You need to reproduce the invariant mass of these products to be sure that W boson produced. And then you need to produce to establish what is invariant mass of all these products. And then to be sure that this is something which is the same in different events, and in this way top quark production has been identified. These things become really complicated. But what we are using the same tool, invariant mass of the products, to find what are the particles which are produced. Okay? Now neutrino, tau neutrino. That's one of the things we could actually discuss in more details. But this is later discovery, and it was almost like obvious that that guy should exist. New tau has been discovered in the year 2000. An experiment in Fermilab with the name DONA, which stands for detector for observations of new tau. So it's kind of D stands from here, detector for observations, and this is nu and tau. So DONA, that's the origin. Now, how the tau neutrino has been produced? Production. So, high energy protons, and this is Fermilab. One is really to have very high energy protons to have a Lorentz boost. Among other things, in collisions with nuclei in the detector, produced DS boson, which means meson, which means the meson which contains charm quark and strange quark. So it's the system of charm and strange. So DS and everything else, among many others. So it's not very kind of often event. Usual D mesons without strange quarks, they're a little bit lighter, so you want still to produce something which is a bit heavier, because then it will have more chance to produce tau lepton and neutrino. So ds decays into nu tau and tau. So that's another mode. And then tau also decays with emission of nu tau plus x. So you have here a production in each of these decay 2 tau neutrinos. So how it happens, you have this charm and S, which annihilates into tau plus and nu tau in this case. Right, so that's the way you describe the decay of ds. So to kind of enhance production of tau neutrino, people use beam dump experiment, which means that you put very dense material as a target, and therefore all the particles like pines, K mesons, which have quite long decay lifetime, they are absorbed in this target before even decay. So in this way you eliminate usual sources of neutrinos and enrich the flux of tau neutrinos. Now, how tau neutrinos have been detected? Remember, one of the criteria is to detect effects of tau of neutrino in some other space-time point and to see if it transfer energy and quantum numbers. So in the donut detector, and that was emulsion detector, so they saw the tracks in emulsion detector. Nu tau interacted with nucleon, produced tau lepton plus everything, and then tau lepton decayed into nu tau, nu e, lepton. I'm not worried about the signs, you can put this correctly. And then nu tau and hadron system. So you might have leptonic mode and you might have a hadronic mode of the decay. And so what you expect in emulsions are tracks with kings. So this is the key point. So what is this tracks with kings? So let's take this mode when you have lepton. In the emulsion you see the following event. One track and then some kind of hadronic jet. Then another track which is thinner and with missing energy. So essentially what you see here, 2 points of interactions and this track with king. That is ascribed to tau lepton, and this is for lepton. So there were events with electron in final state. Actually only 4 events have been detected in the first series of the experiments. So this type of the event, what you observe, point of interactions with some hadron activity, with the track which you can ascribe to tau lepton, which is just millimeter size of the track. So it's very short, and it's important even to use microscope to see these emulsions to check how they were produced. And then you have here electron. So probably I will give you an exercise to compute what is the length of trajectory of tau lepton. So another event when you have hadrons is the following. You have again the point when you produce tau and hadron activity, and then another point when you have hadrons, and again loss of the energy. So this type of the events were produced and observed and identified as production of tau, interactions of tau neutrinos. That was discovery of tau neutrinos. The background was smaller than one event. I don't remember precisely, 0.2 events during exposure time. So that is so-called almost background free, and this is how tau has been discovered. Tau neutrino. Questions?
in the discovering of the 2p quark, when we have two quark and anti-2p quark decaying to B plus and B minus, which is bottom quark, B. So do B plus and B minus each one of them free, or they are related as a meson?
Well, they form, it depends, but most probably they will form some B meson, and already people kind of established that you have production of B meson.
I see.
Which means that big quark is produced and it is hadronized, and of course you do not see three big quarks. They hadronize, most probably form B mesons. The B mesons decay. You measure the invariant mass of the products of B meson decay. Be sure that it is something like 4.555 GeVs. So that's the main signature.
The question is like that they are free, or that we, because
not quarks, B mesons. Yeah, they're flying, and they have some special detectors, silicon detectors, when they see tracks of this of secondary particles from the decay, very close to the interaction point. So B decays, and which is just secondary. So they free in the sense that you form B meson which then decays. Okay? So, and finally, Higgs boson. Again, this guy has been predicted within the standard model, right? So Weinberg and Salami proposed to use Higgs mechanism to give masses to particles in the standard model. That was kind of the final point of construction of the standard model. And there are two important facts, again, that will not be the question during exam, so don't worry. They're just giving kind of brief overview, so these things will not be included. They just give you the general notion. So Higgs boson. It's particle with spin 0 and parity plus. It has important property that it gives masses to all the particles in the standard model: quarks, leptons, W boson, Z boson. And the masses of the particles are organized in such a way that it is proportional or given by the coupling constant of Higgs particle with a given particle, multiplied by what we call vacuum expectation value. So this is coupling. I don't know if my notes. And this is vacuum expectation value. So which means this is the value of the field in the lowest energy state. So the lowest energy state, which is vacuum, is not empty. So it's filled in by this classical field, and everything which actually is within this classical field gets a mass of this form, which means that H is proportional to the mass of the particle divided by V. V is the same for all the particles, but masses are different. So therefore, Higgs are coupled mostly with heavier particles. Now, just few mechanisms of production of Higgs. One is again gluon fusion. So this just picking up just few mechanisms. There are many others. When you have two gluons from proton and proton, so in LHC we have collision of proton and protons, you have two gluons, and the diagram is of the following type: top, top, and top. And then you have Higgs production. So, and it's not accidental because Higgs couples with top quark, and the mass of the top quark, I haven't written, is 173 GeV, it's very heavy. And therefore the coupling with top is the biggest one. Now Higgs decays, and Higgs decays again into most heavier particle, and that is B and B bar. So decay into pair of B and B bar. It's something like 60% decays of the Higgs on this. But what is interesting, that from observational point of view, the easiest mode of the decay was decay of Higgs into gamma. So you have Higgs, and then the diagram of this type, and then gamma and gamma, and this is Higgs, and here are all the fermions which we have in this loop. So this diagram, I don't remember, this is part of the something like 10 to the minus 3. So I think I have it somewhere. Branching ratio is extremely small, so let me check in my notes. Its branching ratio, yes, 10 to the minus 3. Although, which means that in one case out of 1,000 decays, Higgs decay into 2 photons. This is much more often. Here is it's 0.58. But the problem is that it's very dirty decay channel because you have hadrons, and then you need to really recover, to identify that these hadrons come from decay of Higgs boson. For gammas it's easy, and what they did, they constructed invariant mass of 2 gammas. Again, the same story, and what they saw, background, and then the peak at 125 GeVs. Let me put it still, it's not so, something like this. So they saw the peak with mass 125, so this is the Higgs mass. Again, this will be repeated in the course of the standard model. Although many things can be discussed even without even introduction of the standard model, as you see, so most of the things we have discussed already before. The interesting fact, which we don't understand yet, the top has coupling constant, which is 1. Why? Something. All other fermions have much smaller couplings with Higgs. So there's something special in top quark, and there are some mechanisms of symmetry violation related to top quark. And actually, top quark produces some renormalization effect because of this big coupling for the Higgs mass. And so that should be taken into account. And Higgs, of course, has a coupling with W boson, with Z boson, but these things are within the standard model framework. Okay? What I would suggest you, just for you not to be confused, create a table of your table of particles, of elementary particles. There are different suggestions. You can write this in your way if you want, but just to understand what are dimensions. So there's one dimension which is along which we have weak interactions. There's another dimension which is color. You have color. And then there's a family dimension. And we have 3 families. So what is interesting, and it was a great idea of Patti and Salam, that maybe leptons can be considered as the 4th color. So we have 3 colors, right, in QCD. And we have leptons, and we have correspondence of quarks and leptons. The idea was that why not to have to consider this leptons as just fourth color. Of course, it should be violation of this fourth color, so that total color group is broken up to SU3, and then you have leptons which have no these additional interactions. So put the table of this type. So say you have U quark, D quark, so one color. Then you have here U, D another color, then U, D the third color, so color is in this direction. Then you have U, D, here you can put, so this is U, D, then charm, S, then you have here top, B, so this is family direction. Huh? So this is color direction. So here is this direction is weak interaction direction. So you have transition between U and D here in this direction. And now you can put leptons here. So you can put here, for instance, mu and E. Here you can put muon neutrino and muon. Here is tau neutrino and tau. So what is behind this is a good question. Behind this classification. So last topic which I will discuss, I thought that I will spend some time even today, is the symmetry. Let me just take probably 5 minutes again to recall a very general thing. And if you have conceptual or misconception, confusion about conceptions, you can always go to this simple example about the symmetries and just to check your understanding. Okay? And particle physics. So let me write the circle, and I start with example. Let me write the circle. It has symmetry, right? Let me write the question for this circle. So if this is y and this is x, then the question is x squared plus y squared equals a squared, and a is the radius. How to formalize? And clearly we have some symmetry, right? Some symmetric, just to see this. How to formalize the symmetry? So, for instance, if you start to rotate this circle, nothing changed, right? You will not recognize any difference. Or you can rotate yourself, so you can look at this one, but you can look at this one, and you will have the same plot, right? This means that symmetry always related to some transformations, right? Either we are making this rotation or we rotate the coordinates, rotating ourselves. So here we have invariance with respect to rotations, right? And in very general, symmetry means invariance with respect to some transformations. You transform, nothing changes. The shape is the same. Right? So to be more formal, we can do the following. We can do transformation of coordinates, rotating by the angle alpha, for instance. So that's rotation. And then we have new coordinates, which are related to the previous by these relations. Right? So this is rotation. Now, if you insert x and y to this formula, you will get x prime square plus y prime square equals a for all values of alpha. Alpha is what we call parameter of transformation. Agree? Square. We have already discussed these things in terms of Lagrangians. Remember, at some point I introduced already this. But again, all this will be repeated many times when we will discuss different symmetries. So I'll just optimize this discussion, because everything is the same. So we have some transformation. So this is transformation. This is form of the equation, form of what we are studying in original coordinates. Now, we do transformations, and we find what is this form of this equation after transformation. And what we see that it has the same form in terms of new variables, right? We change variables doing transformations, and we get that the form doesn't change. So this is how we formalize or express the symmetry. We start with something, make transformation, and check if the form in terms of new variables changes or not. The equation is the same both in initial and final coordinates. This is simple, trivial, but surprisingly when we go to more complicated situations, sometimes you are confused. So, this means that to define symmetry, we need to define transformations. This is important. Define symmetry means to define transformations. So, sometimes we are having some theory. We can introduce some transformations and then check if our theory, our Lagrangian, is invariant or not with respect to this transformation. This is typical procedure which we are doing. Well, what is interesting that symmetry almost determines the shape of this equation. This is power of the symmetry. If I say that I want to find some figure which is invariant under these transformations and put condition that I want to have lowest order in power of x and y, I almost coming to this expression. Right? So this means that just formulating the symmetries or set of the symmetries, I essentially can define the theory, which means Lagrangian or Newtonian, my theory, up to some coefficients, or parameters, coupling constants. Okay? So this actually, another point here is that this figure has actually additional symmetry. What is the symmetry? In addition to rotation. Yes, you may have reflection, right? Reflection of the symmetry, which means that you can define another transformation, x equal to minus x and y equal to y, which cannot be reproduced by this. So, your theory, this is our theory, right, in this example, may have different symmetries, and they have different consequences, different physical consequences, as we will define. And finally, what is violation of the symmetry? We can violate the symmetry by adding some term. So you can have x squared plus y squared plus delta y squared. Delta some coefficient equals what? A. And this way, we will break this symmetry. But we will not break this one. So this is a simple example, right? And we will continue with particular symmetries on Monday. So, think about this example. Every time if you have some kind of problem to understand, come back to this example and so this is trivial, right? Symmetry is always related to some transformation. Symmetry means invariance of the form with respect to transformations. This invariance leads to great physical consequences, many different physical consequences, as you will see. Okay?